Well, to make the editing easier, I'll start that again. I'll read you the introduction. So welcome everybody to the Friday morning Euro seminar series. We have John Ellis with the U.S. Geological Survey going to speak to us today. And here to introduce him is Dr. Bridget Scanlon from our own BEG.
Thanks, Brian. And we're delighted to have John Ellis present today his work on land surface groundwater nexus. John and I visited during COVID, and he described some of his regional modeling and the uncertainty analysis and subsidence work, and I was extremely impressed with their program and what they were doing. So it's great to have him today presenting these results, and the report should be coming out shortly in November, which is marvelous. So John is a professional geoscientist and a supervisory hydrologist at the USGS Oklahoma Texas Water Science Center in Houston, and he joined the office in Houston in 2019 and leads a team evaluating water quality, land subsidence, and groundwater level changes in the Houston area and North Texas Gulf Coast. Before joining the office in Houston, he worked at the Oklahoma Water Science Center and as a hydrologist, leading aquifer studies and developing models on integrated surface water and groundwater resources and assessing effects of future climate variability on aquifer and reservoir storage in Oklahoma. John has a BS degree in geosciences from the University of Texas at Dallas, an MS in environmental science from Hardin-Simmons University, and an MS in hydrogeology from the University of Alabama. University of Alabama hasn't been doing too well lately. John, I hope you're not too depressed.
I'll make it, thanks.
So thanks so much, John. Go ahead and share your screen, and looking forward to your presentation.
Yeah, absolutely. All right, so I hope everybody can see the slides here okay. Thanks for the introduction, Bridget. I'm John Ellis with the U.S. Geological Survey, here to talk to you about the connection between groundwater changes in land surface elevation and changes in groundwater altitudes. So I know many of you in here deal with water topics or have or know people that do or are familiar with kind of that arena. So this talk kind of ties a little bit into geology, but also into that water component as well. And I'm going to present a case study on Brownwood, which is in Baytown, Texas, in the greater Houston area, and kind of describe some historical events based on changes in groundwater levels. So some of you may be familiar with the story of Brownwood. The subdivision gained national attention back in the 1960s, really beginning in 1961 when a hurricane hit the area, and kind of the long-term plight of that subdivision became known. So I'm going to use a data-driven perspective to walk through the major events, generally starting from about the 1940s to about the 1970s. So here on the slide, you see the location of Brownwood, again, there in Baytown and in the greater Houston area. So it's basically a little bit east of the downtown Houston area over there on the east side of Harris County. And you see it there on the slide on the inset there in black, there in the Houston Ship Channel. So the story begins back in 1918 when the Humble Oil Company, which was later acquired by Standard Oil and then later on ExxonMobil, decided to build a refinery in Baytown that was completed in 1920. So you fast forward to 1937, and Humble Oil purchased the future subdivision's land from Edwin Rice Brown, and Brownwood was then founded the following year in about 1938. So the subdivision was built to house the professional and the executive staff of the refinery. It was a very, very nice neighborhood. And it was situated on a peninsula extending about a quarter mile into the water there in the Ship Channel, surrounded by Scott Bay, Crystal Bay, and Burnett Bay, directly across the bay from the San Jacinto Monument. So that's the location there for our talk today, is that Brownwood subdivision. So you see the aerial photo of Brownwood in 1944, and this image shows Brownwood about 6 years after having been founded again by the Humble Oil Company. And the land surface at the time, in 1944, was about 10.5 feet above sea level when it was originally purchased and development started there in the neighborhood. Oops, one. So this shot shows the upper part of the neighborhood. Again, you can just see that land surface area. We got that peninsula there between Crystal Bay and Burnett Bay at the top. So fast forward about 9 years, and this slide shows the Brownwood subdivision in 1953, about 3 years before the subdivision was completed. So that land area looks similar to the 1944 land aerial photo that you saw, but not everything was the same. If you compare them side by side, there are some noticeable changes here. So at the bottom of the screen there in the 1944 image, you see that marshland area. But by 1953, if you look on the right side of the photo, it's submerged. And I've highlighted that there in some blue shading on the right side of the screen. 1953, again, compared to 1944. If you look at the 1944 land area there, again, you see that marshland area, which I've highlighted here for the 1944 photo. And by 1953, you no longer see that area either. So something was going on here that was causing the subdivision to lose land area as far back as the 40s and 50s. Now I'm going to move forward to 1978. By 1978, the change in the land area was unmistakable. The 1944 land area I show there by the black outline of the area filled in with the blue shading. So obviously there's a very big difference when you fast forward to 1978. And by this point in time, the subdivision was barely above sea level. A raised perimeter eroded and failed to keep out the water, and rather, when the subdivision flooded, it just turned it into a bowl and kept it in. And many acres have been lost around the perimeter of Brownwood, and the bay water had reached the perimeter road in multiple areas. So obviously very, very big change when you look at 1978, whether you're looking at the southern part of the neighborhood, or if you look up here at the upper part, again, you see much the same thing, that substantial loss in land area around the perimeter of the subdivision. We fast forward to present day, to 2022, and it's no longer a neighborhood. This is now the site of the Baytown Nature Center. As you can see there, looking at the photo, the land area is still much the same. However, there's a number of rivers and streams that run through that area that connect the bays. And if you look up at the northern and the upper part of the neighborhood, what used to be the neighborhood, you see much the same thing. So this is the Brownwood Nature Center, and you can go there and actually drive through this and see what used to be there in the neighborhood, and they turned this into a bit of a park. So the question is what happened? Well, how did this neighborhood sink into the ocean, as you've seen from those photos? So if you look here on the screen, you see on the right side of the screen me holding a leveling rod. If you look at the numbers on the slide, those are the dates and the elevation of the neighborhood at that date. So as you can see from that leveling rod, there's quite a bit of change there in the land area. You can see it for scale, so me holding it right next to it. So that loss in land area, that was due to a process called land subsidence, which occurs due to the compaction of fine-grained sediment, which are generally silts and clays in an aquifer system with declining groundwater levels. And the groundwater levels decline due to pumping in the aquifer system. So land subsidence can be difficult to discern because in most cases, the entire land is sinking together, and without specialized equipment, like an extensometer, there's not any way or any point to compare it against. So we know how much land subsided in Brownwood because there's a USGS benchmark, PTS 185, that was monumented back in 1915, about 1,500 feet east of the neighborhood. And you know that's there because the level rod on the right side of the screen, that photo is resting on it. And that benchmark was reoccupied many times through time, and elevations were taken there. And for anybody that's not familiar with spirit leveling, you take the difference of leveled elevations from each leveling survey at the same benchmark, and then you subtract those elevations through time. And then from there, you can construct a time series plot of the cumulative subsidence. Now, the leveling lines are run at this benchmark and many others by the National Geodetic Survey that they were very precise, typically first and second order leveling. So this is very good information, very accurate information that we were able to obtain for subsidence in this area. And as you know from those aerial imagery I showed you earlier, the land subsidence did not happen overnight in Brownwood. Rather, it occurred over a long period of time. So with that in mind, let's revisit some of those aerial images again, except this time I will show the groundwater levels and the cumulative subsidence from this benchmark on each slide. Okay, so we start in 1944. So on the bottom right side of the slide here, I've added a figure that shows the amount of land subsidence in Brownwood, and that's in the red, the dashed red line, and the circles are the actual benchmark, the reoccupations, the leveling that was done, elevations that were taken there on the right side of the slide. And then the water levels in blue there through time. So you can kind of see both of those paired together. So groundwater levels, looking at this early on in time, we're about 40 to 50 feet above land surface, or below land surface around 1923. So very early on, you already had a little bit of decline in groundwater levels from what was originally near land surface. And that's because in 1920, groundwater use began in the Baytown area after the establishment of the Humble oil refinery that I'd mentioned previously. Now that oil refinery is located only about a mile from the Brownwood subdivision. So by 1923, groundwater levels there were about 58 to 60 feet below land surface. So again, you see that on that far left side there on the slide is that measurement. And that was a decline of about 30 feet since 1915, based on an increase in groundwater use to about 5 million gallons per day in the local area. However, when you fast forward to 1944, which is the land area shown here on the slide, with all those wells in service, the groundwater level had declined to about 130 feet below land surface, based on a groundwater use of about 15 million gallons per day there again at the refinery in the local area. So when nearby leveling surveys were complete that same year in 1944, the results showed that the land surface had subsided by about 2 feet already since 1915, just as residents were in the early stages of moving into the subdivision. So the land subsided about 1.6 to 1.9 feet for every 100 feet of groundwater level decline here in the early stages. Okay, we're going to move on to 1953. So now moving on to 1953, at this point, Brownwood was about 3 years away from being built out and the subdivision being complete. Now you'll notice the blue shaded areas on the slide here, and those low-lying areas that were the areas that were above water in 1944 and are now submerged 9 years later. When I showed that 1944 to 1953 comparison earlier in the presentation, you saw that same thing. It's just here again on the slide with a few other areas that were harder to tell from that earlier land, that other earlier version that I showed you. And those former lands slipped into the bay because the land subsided about 1.5 feet since 1944. And that was again due to the subsidence from the groundwater levels having declined about 35 feet since 1944. So at this point in 1953, groundwater use was about 23 million gallons per day in that local area, the majority of which came from use at the refinery about a mile away. So to note, if you average that out, the groundwater level declines averaged a bit under about 5 feet per year since 1925. So with that said, again, that 1.5 feet subsidence since 1944 masks a much more important number, which is 3.7 feet. And you see that there on the slide. Since 1915, since that first benchmark was monumented, there was about 3.7 feet of subsidence all the way up to 1953. And that means that that original 11.8 foot above mean sea level elevation in the neighborhood was now about 8 feet above sea level. So very big difference there early on. And with all of that said, it's important to note that the residents and the general public didn't yet know about land subsidence or really what caused it at this time, back in 1953. Now, in 1953, only one scientific paper essentially had been published on land subsidence in this area back in 1926 by Wallace Pratt, who was the first geologist hired by Humble Oil in 1918. And it documented the sinking oil derricks and the platforms at Goose Creek, that oil field about 7 miles south of Brownwood in that same general area. But the first paper that was definitively linked subsidence to declining groundwater levels wouldn't be published until the following year in 1954 in the Journal of Economic Geology. So while the land was sinking, there really was not much understanding about the process and what was going on. So let's move on to 1962. So as you can see from the slide in the shaded areas, by 1962, real changes were starting to happen to the shoreline in this neighborhood. And that loss of land surface area was really starting to become noticeable. And if you look at the shaded areas, that peninsula to the southwest basically slipped entirely under the waves, and water had now reached the perimeter road in the middle of the subdivision over here on the right. And right around this same time, Brownwood started to be affected by storms, hurricanes, and tropical storms that were happening in the local area. So in July 1959, Hurricane Deborah made landfall between Freeport and Galveston, and parts of Brownwood flooded essentially for the first time, and some homes received as much as 2 inches of water. So overall, Hurricane Deborah didn't cause a whole lot of damage, and the flooding was fairly minor. However, 2 years later, in September 1961, Hurricane Carla resulted in substantial damage to the Brownwood, estimated at $3.5 million in 1961, and as much as 10 feet of water entered homes in the subdivision. As you can see from the newspaper heading there from the Baytown Sun, I mean, the neighborhood was essentially declared a almost complete loss. And by the time of Hurricane Carla in 1961, Brownwood had now subsided about 5.1 feet and was an average of about 6.7 feet, or about 6.5 feet above sea level. So between 1906 and 1943, the land subsided about 1.6 to 1.9 feet for every 100 feet of groundwater level decline. But between 1959 and 1964, the land now subsided about 4 feet per 100 feet of groundwater level decline. And as I mentioned before, in 1954, that journal article that linked land subsidence and groundwater level changes had been published. And in 1959, a second one was published that validated the conclusions from that first paper. Other than that, though, there was very little else that was written on land subsidence for a little longer. Yeah, we move on to 1966. So during those intervening 5 years from the previous slide I showed you, the land subsided about another foot, as you can see there on the figure on the screen. And at this point, the mean land surface elevation above sea level was now about 5.6 feet, or less than half of that 1915 elevation of about 11 feet above sea level. And because the groundwater levels had been continuously declining, this subsidence was inelastic or permanent. And this was definitely a turning point for this neighborhood. I mean, to put that 5.6 feet of elevation of sea level in comparison, a large freighter can generate a wake, pretty substantial wake near that amount. And storm surge from a major storm can easily be 10 feet or more above sea level. And again, this neighborhood at this point is average of only about 5.6 feet above sea level. So the hurricanes and tropical storms, unfortunately, continued for the neighborhood. In 1967, a third hurricane, Hurricane Beulah, hit the Texas coast in September of that year. And it caused flooding in Brownwood. Now, the last storm event was Hurricane Carla in 1961. So it had been some time since a major flooding event occurred in the subdivision. The image there on the right shows the flooding across the perimeter road during the storm, which is right here. You can see that right here where it's pointing to on the slide. Now, you can see that subsidence based on the loss in land area on the perimeter, but if you take a cross section of it, this is what you see for the 1915 elevation. And by 1966, This is what you see now in that cross section through the interior of the neighborhood. So you can see that flooding that I've highlighted around the perimeter, but the loss of land elevation in the middle of the suburb, it was very real. And again, large land change since 1915. Now we move on to 1973. So by 1973, the neighborhood's plight had gained national attention. The subdivision had just been hit by Tropical Storm Delia in that September 1973, and that had occurred on the heels of the Valentine's Day flood in February 1969 and those 3 prior hurricanes I just discussed earlier. So that Valentine's Day flood in 1969, it flooded about 150 homes in the subdivision, and damage was estimated about $250,000. You move on to Tropical Storm Delia in 1973, and it flooded about 140 homes, and it damaged another 250 homes, and it caused about $2.5 to $3 million in damage. And there was water up to about 4 feet in some of the homes in the subdivision. So at this point in 1973, Brownwood had subsided at 8.2 feet, and it was only about 3.6 feet above sea level. So to note, I mentioned that perimeter road in some of the other slides, and that to help with some of the flooding, that perimeter road had been raised and elevated to an elevation of about 7 feet above sea level about 6 months prior to that tropical storm in 1973. And you can see that here on the slide. This is a shot of that perimeter road right here in about the middle of the subdivision where this perimeter road is. But there was 2 problems with that approach of elevating that perimeter road, trying to help save the subdivision from flooding. First, there was no way to anchor that perimeter road to ground that wasn't already sinking. So as the subdivision continued to subside, the elevated perimeter road sank with it. And the other problem is that even at the elevation of about 7 feet above sea level, that road had been maintained, it still wasn't sufficient to protect the subdivision. Back in 1959, when the mean land surface elevation was right at about 7 feet for the neighborhood, Hurricane Deborah had resulted in the millions of dollars flooding. And the third problem with this raised perimeter road was that if a storm tide went over the road, that water would remain trapped in the neighborhood, inside the perimeter of it, and turned it into a bit of a bowl, even with pumps operating. And that's precisely what happened during Tropical Storm Delia that same year in 1973. There was as much as 5 feet of water remaining all around the inside of the perimeter road in the neighborhood that was trapped there after the tropical storm and had to be pumped out. So regardless at this point, the suburb was now an average of only about 3 feet above sea level, 3.6 feet. So this shows you a well-known photo that's been published many times in Subsidence articles that I have there on screen. This house was built in the early 1940s, and it rested on land about 6 feet above sea level at the time it was built, but it subsided about 7 feet by the time this photo was taken in 1973. And due to the subsidence around the house, it had essentially become surrounded by water, by bay water that separated it from the subdivision land. And you can see where that's at. It's over here on the northwestern part of the subdivision, surrounded by this essentially bay water. All right, we move on to 1978. So by 1978, the end of the subdivision was near. The mean land surface elevation, you can see there on the slide, was now only just 2.6 feet above sea level. And that perimeter road was about, at this point, about 5.5 to 6 feet above sea level. So this means that a hurricane or tropical storm were no longer required to flood substantial parts of that neighborhood. And in fact, in 1979, houses around the neighborhood flooded in 2 separate events the same month in April of that year. But a larger flooding event happened during Tropical Storm Claudette in July of that year in 1979. And that tropical storm made landfall near the Texas-Louisiana border and resulted in high tides in the Baytown area. And you had flooding to about 180 homes there in Brownwood. And then finally, Hurricane Alicia in 1983 resulted in abandonment of the neighborhood. So when you look at that slide on the right side of the screen, you'll notice the historical groundwater level minimum of about 290 feet occurred back in 1972, about 6 years prior. And the subsidence effectively been halted by 1978. But there was about another foot of subsidence that occurred between 1973 and 1976, even after groundwater levels were rising. And that's because of residual compaction that occurred due to the slow equilibration of the groundwater levels in the fine grain and the coarse grain units. So you had that continued compaction even though water levels rose. So we go back to that cross-section view that I showed you earlier. Again, this is the 1915 land surface elevation. And then you see the 1966. And then you see the 1978. And if you look at the upper part of the neighborhood here, you can see the original 1944 extent, and you can see in 1978 what it looked like. And the last photo, historical photo I show you here is that same perimeter road on the upper part of the subdivision over on the right side. You can see that where it points to here. So that photo shows that perimeter road in 1979, and you can see how close to sea level it is by this point. Okay, so let's move on from the history of Brownwood. Let's take a look at those mechanics behind land subsidence that cause Brownwood to subside more than 9 feet. So as I mentioned before, land can subside as a result of groundwater pumping and aquifer units that include fine-grained sediment. So think silt and clay. So the clay layers compact versus sand layers because sand is more transmissive and less compressible than the fine-grained sediment. So the silt and clay layers, which are often interbedded in the larger aquifer unit, dewater more slowly compared to the sand layers. And the theoretical basis for compaction of subsurface material is based on Terzaghi in 1925, that theory of one-dimensional consolidation. So on the slide here, I show 4 columns of aquifer material. So starting with that first column on the left, that shows you the aquifer prior to the decline of groundwater levels. So the water stored in the silt and the clay layers prior to that depressuring, it provides kind of interstitial pore space support to the skeletal matrix of the silt and clay grains and to the aquifer unit. So if you look at that second column from the left, moving over 1 column, subsidence can occur as a result of long-term groundwater level declines. And those declines result in a depressuring or a decrease in the hydrostatic pressure or the hydrostatic stress. It creates a load on the skeletal matrix, the sediments of the aquifer and the confining units. So that decrease in hydrostatic pressure results in an increase in effective stress, resulting in subsidence. And again, you see that on that second column. And if you move over to the third and the fourth columns from the left, you see that as ground level increases, then an effective stress decreases, and there's a rebound in land surface that can occur if the compaction is elastic. And if the groundwater levels decrease, then the compaction continues. So you may wonder, when is land surface recoverable? That compaction, when is that compaction permanent? So if the effective stress is less than any previous maximum effective stress, which is generally the lowest groundwater level, called the pre-consolidation stress, then the compaction is elastic or it's recoverable. If the effective stress is greater than the pre-consolidation stress, then the compaction is inelastic or permanent. So taking a look at that Brownwood subdivision and the Baytown area as a whole, I mean, now that you've seen some that subsidence in Brownwood, it's important to realize that subsidence did not affect just Brownwood or even just Baytown. In fact, it's substantially affected the entire greater Houston area over the last 115 years. So it's affected roughly about 4,200 square miles of land area, which have subsided at least 1 foot since 1906. And that compares to about 2,500 square miles of land area that have subsided 1 foot by 1973. And about 3,600 square miles of land that has subsided at least a foot by 1987. Now, we know the land has subsided through a combination of 3 different ways of measuring subsidence compaction. And those include leveled elevations at benchmarks, global positioning system stations, and borehole extensometers. And I will get to those and describe those here briefly. So looking at the leveling data, leveled USGS and National Geodetic Survey benchmarks, those form the primary historical network of regional geodetic control in Texas, particularly in southeastern Texas, where leveling has been performed since 1906. So if you look at the original line that ran in 1906 through the greater Houston area, this line was ran in 1906 by NGS, and it began in Smithville, Texas, and it ran east along railroad tracks adjacent to the future site of Interstate 10, all the way to modern day downtown. And then that line turned south and ran along a railroad adjoining the future side of Interstate 45, all the way down to Galveston Island. And you can see that in red there, that leveling line on the slide. There's about less than 100 benchmarks are monumented during this 1906 line. However, only a few of these still exist due to the growth of the city area. As that city area has grown, and of course, Houston has grown substantially in the last 100 years, those benchmarks, unfortunately, were destroyed through time. Now, I don't show it here on the slide. There was also in 1915 leveling effort by USGS, and it covered much of southeastern and central Harris County. And those benchmarks that were established as a part of that those USGS lines, those were used to establish that subsidence at the Goose Creek oil field that occurred between 1918 and 1925. And those benchmarks were subsequently leveled a few times over the years. However, the majority of those, again, were also destroyed because of the growth in the land area of the city of Houston area. Okay, so this shows the 1918 NGS leveling line, which began in Sinton, Texas, and it ran northeastward across Brazoria County and then northward to downtown Houston, and then northeastward through Liberty County. And you can see that there in green on the slide. So that's the 1918 line. Okay, and then this last one I'll show as far as the leveling lines, this is the 1932 to 1936 lines. So these were no longer just single lines. There were a number of lines that were ran here by NGS across the greater Houston area. And the 1932 lines began north of Houston in Palestine, Texas, and they ran south along railroad tracks adjoining the future location of I-45, all the way to downtown Houston. And then from there, they ran through southeastern Harris County and Galveston, Fort Bend, and Brazoria counties. So I show you these so you can see where the original data was collected, or these original benchmarks were monumented between 1906 and then 1936 in the greater Houston area. Now, there were many more benchmarks that were established, actually thousands of them, beginning in 1943. But these leveling lines show you the oldest data here in the greater Houston area. So this slide shows you the GPS network, and this is the second way to estimate subsidence other than using spirit leveling. So this shows GPS stations in the greater Houston area with at least 5 years or more of data. And these sites are part of the HoustonNet, which is operated by University of Houston and the Harris-Galveston Subsidence District, as well as a few other partners. So this this network has largely replaced spirit leveling due to the fact that spirit leveling surveys for the entire net surveys were millions of dollars when those were conducted. Where here, for less money, you can end up with a spatially distributed network of real-time, essentially real-time vertical displacement data all the way across the greater Houston area. Now to note, there's 4 of these stations that are actually on the extensometers, the inner pipe of the extensometers that I'll get to here in a second, and they provide stable reference stations, stable points of reference for the Houston-Galveston region, regardless of the subsidence that is occurring. So this is the third way you measure subsidence, and it's through use of borehole extensometers. And you could say that a borehole extensometer is basically a deeply anchored benchmark in the earth. And to install an extensometer, a hole is drilled to a depth where the geologic sediment is considered to be stable. And then an inner pipe is installed down that hole and situated on the cement plug at the bottom of the well. And the compaction is recorded as the distance between the inner pipe and land surface, recorded by a F recorder, an analog recorder that looks like a seismograph, or in more modern times by a shaft encoder. So this graphic here shows you where in the greater Houston area we have these extensometers, and there's 14 extensometers at 12 sites. So the first extensometer was installed in September 1959 at the city of Houston at their former East End water plant. And then the second was installed in 1962 there at the Johnson Space Center. And the next 11 were installed between 1973 and 1980. And as you see there on the bottom left of the screen, those show you the altitude that these extensometers are anchored, and they're not the same. And that's because they are anchored below where the majority of water use occurred in the greater Houston area from what depths they occurred. So, for example, you have there at Baytown, you have two extensometers. You have the Baytown shallow and the Baytown deep extensometers. One of them is anchored around 500 feet below an ABD 88. One is anchored at about 1,200 feet, and those are anchored to where they can capture the subsidence happening locally in that area below where the major zones of water production are. And then you can also subtract the compaction recorded by those, difference them to get the compaction occurring in different zones and different areas below land surface. So bringing the discussion back to Brownwood, why is it that Brownwood and Baytown sank over 9 feet, nearly into the sea, but other areas did not, even though substantial groundwater use occurred as long or longer than the area around Brownwood? That's the question here. And part of that answer lies in the spatial distribution of groundwater use, of groundwater pumping. So on the screen here, I show 4 of the 5 major areas of historical groundwater use. From the left, you see the historical Katy area. In the middle there, you see the Houston city area around 1950s outline there in gray. And then moving to the right, you see Pasadena, and then you see the Baytown area, and at the bottom there in Galveston, you see the Texas City area. So we look just briefly at the water use here. In that historical Katy area, as those historical reports describe it, this had the second largest amount of water use in the greater Houston area from 1900 to 1990, and that had a peak of about 172 million gallons per day of water use in 1967. So that is quite a bit of groundwater use there. However, it is very spatially distributed over the largest land area relative to those other areas of historical water use. Now, if you look at the pumping distribution in the historical Houston area, again, that shaded gray area is what the Houston city limits look like in about 1950. So there's a historical maximum about 255 million gallons per day of water use by 1980. And that municipal use, was about 75% of that total groundwater use. Now, if you look on the slide there, those black dots represent large sources of pumping, or generally our individual wells. So as you can see there, the city of Houston began spatially distributing its well network around the city, and that began all the way back in 1919, when the 3rd and the 4th municipal water plants, which were the South End and the West End stations, were constructed. And that was done on purpose to avoid the drawdown of those wells forming intersecting cones of depression and merging together to form one large area of groundwater level decline. Now that largely did happen anyways, but it delayed the occurrence of that happening, and it lessened the drawdown overall because they spatially distributed these sites. And on the screen here, I show you an image of the first municipal plant in Houston. This is the central water plant for the city of Houston, or the former central water plant, which was previously called the Houston Waterworks plant prior to 1906, when this plant was purchased by the city of Houston. And in this slide, this image shows you an image of the 1915 South End water plant that I described briefly earlier. And this is on the north side of the Houston Museum of Natural Science. If you've ever been to that museum, all you have to do is walk around to the north side and you'll actually see this plant. And there's there's a plaque in front that shows the site diagram and kind of describes the history of this site. So if you ever get a chance to go there to the Museum of Natural Science, look for the station on the north side of that museum. So if we move over to Pasadena, so this slide shows the historical Pasadena area during about 1950. So the historical maximum water use was about 126 million gallons per day by 1968. So it was a bit less than the historical Houston area, but all of that water was for industrial purposes. And if you look at the physical land area compared to the Katy area, the Houston area, the historical Houston area, the groundwater use was much more concentrated. And then finally, we take a look at the Baytown area. So this shows the historical Baytown area again during the 1950s, and a historical maximum of about 32 million gallons per day of water use occurred in 1972. So much less than the historical Houston area and that's historical Katy area. And all of this water use again was largely for industrial purposes. Now, the majority of this early time water use was from the Humboldt oil refinery, and that water use was not only concentrated in a small area in Baytown, but particularly there at the location of the plant, it was concentrated in basically an area of 1 by 2 mile area. So this water use was even more concentrated than in Pasadena, and it was also vertically concentrated as well. Nearly all that historical groundwater use in Baytown occurred from less than about 600 feet below land surface. And there's this highly productive sand called the Alta Loma sand from about 400 to 500 feet below land surface in the Baytown area. So almost all of that water use occurred from that 100 to 150 foot interval. And then there's also another thing to note. Subsidence in Baytown wasn't due just to groundwater pumping in Baytown. That Alta Loma sand was also screened essentially as you move west of there in the Pasadena area, and groundwater level declines in other parts of the aquifer, to include the Evangeline aquifer, also resulted in declines in the Evangeline aquifer there in Baytown, even though water use was not occurring from the Evangeline and Baytown historically. So just to wrap up the discussion on the pumping distribution, if you break out that amount of water use per land area for each of those areas, as you can see, the Baytown groundwater use was very highly concentrated compared to the Pasadena area, the Houston area, or the Katy area. Much more groundwater use concentration there. Again, a large amount of which occurred only a mile away from that Brownwood subdivision. And then again, Baytown was also affected by Pasadena groundwater use. So I'll just briefly go through a couple of slides for showing the historical time series of subsidence, and then looking also at the groundwater level declines from early on to present day. So this slide shows the Katy area that I showed you earlier as far as the groundwater use and the distribution of that pumping. So there was about half a foot of subsidence per 100 feet of groundwater level decline early on until about 1943. And then later on, after about 1964 to 1973, you had about 3.2 feet of subsidence per 100 feet of groundwater level decline. And this is the subsidence you see on this slide is there at benchmark Y7, which is one of the few remaining 1906 benchmarks in the entire greater Houston area. And USGS leveled this benchmark in the summer of 2021, so it has a time series leveled elevations for about 115 years. So looking at the historical Katy area, similar to the Baytown area, most of the wells in this area early in time were generally screened less than about 500 feet below land surface in the unconfined to the semi-confined parts of the Geological aquifer. So there was a large amount of water use. Remember that 160 million gallons per day peak of historical use, but the wells were spatially distributed to drew that water, and there was unconfined to semi-confined conditions, which resulted in relatively small amounts of drawdown. Also, a thing to note is in this historical Katy area, you have the proximity of the recharge zone that is shown on the top right of the screen here in that dashed line. And that because of that increased amount of recharge there in that area and proximity to the recharge zone to the outcrop zone, the sediment there is sandier and it contains less fine-grained sediment than the down dip areas where the Beaumont clay is present, which is at those other sites. The Beaumont clay is present at all those other sites, and it has substantially much larger amount of clay, which controls, to a large degree, the compaction that occurs. So looking at this, if you translate those clay percentages, that clay amount to a percentage, in the Chico Aquifer in this area right here in the Katy area, about 75%, it's about 75% sand. Whereas if you move east all the way over to Baytown, only about 40% of the aquifer is sand type marine sand material. And if you look at the Evangeline Aquifer, it's generally about 30 to 45% across the greater Houston area. Now, if you go back over to that historical Houston area here, you see about twice as much subsidence per 100 foot of groundwater level decline from 1906 to 1943. And then by 1964 to 1973, you had about 3.7 feet of subsidence per 100 feet of groundwater level decline. So there's quite a bit more there than the Katy area. And again, that's because although the groundwater use was spatially distributed, there was more of it, and there was more fine-grained sediment in the aquifer column. And then finally, we go over here to Baytown, and if you look at those numbers from 1906 to 1943, there's about twice as much subsidence per 100 foot of groundwater level decline than there is in the Houston area historically, and 4 times as much as there was in the Katy area. And by 1964 to 1973, we're looking at almost 5 feet of subsidence per 100 feet of groundwater level decline. So very, very substantial amount of decline there of subsidence for a fairly small amount of groundwater level decline. So just in the last few slides here, just have a quick look at kind of the third part of looking at these subsidence rates and why they're different across the greater Houston area. So the diagram on the slide here on the right, you see a cross section of the aquifer units and the lithology down to about 700 feet below land surface. So that Altaloma sand, that productive sand there, is where these example wells are screened, and these are actually from the what used to be the Humboldt oil refinery, now the ExxonMobil refinery, from 2 former wells that are long since destroyed on that site. So these wells were screened in the Altaloma. However, there were also many wells that were screened in the Beaumont clay. And again, because you had large amounts of that clay, as groundwater is pumped from that area and groundwater levels decline, that depressuring occurs. Then you start getting compaction due to those many clay layers sandwiched between the sand in this area. So if you look at a deeper version of this, this strat column is showed at the Baytown extensometer. You can see in red there's a lot of clay in this aquifer column there in the Chico Aquifer. So we're lucky to have a lot of co-located wells that show you the groundwater levels through time at the same site. They're screened across different intervals of the sand, silt, and the clay there at the site. So you notice that the groundwater levels, the pattern is the same in almost every one of these, even though the decline and recovery is a little bit different at different intervals. Now, if you look at the Evangeline Aquifer, those last 2 wells at the bottom of the screen, I mentioned before that there was effectively no groundwater use in Baytown below about 600 feet below land surface, about 550, 600 feet. But if you look at the declines in these bottom 2 wells, you'll see that they're almost the same as the other wells above them, even though that groundwater use didn't occur. And again, that is due to the groundwater use in Pasadena that was propagated down dip all the way over to Baytown. So this is why Baytown had one of the highest rates of subsidence and overall cumulative compaction compared to all the other areas. It's because the decline in groundwater levels in other areas like Pasadena affected Baytown. So just as some takeaways here, number 1, subsidence can result in increased susceptibility to flooding and structural issues. And what goes down doesn't always come up. Much of the subsidence in the Houston historical area, the greater Houston area, has been permanent because of the continuous decline in groundwater levels. So it's essentially been inelastic or permanent, and it will not recover back to its previous elevation. And just to recap that discussion I've had just more recently on the slides, the subsidence rate, the total amount of subsidence, it depends on that groundwater use distribution, those declines, those groundwater level declines, and then the properties and distribution of the fine grained sediment. Okay, just a last slide shows you some online resources. Much of this material and discussion will be printed in the Golf report that'll be out tentatively on November 10th next month. And additionally, there are a number of resources as well, a number of USGS reports that have been published through the years. There's more than 85 of them, and those are almost all available online on the USGS webpage. So with that said, thank you for your time, and I'm happy to take any questions if y'all do a question and answer period.
Yeah, thanks, John. It was a great talk. I learned a lot and really synthesized a lot of material there that I've sort of heard bits about over the years. So I really enjoyed that. We definitely have time for some questions. So if folks out in the audience would like to unmute themselves and ask, or you can also put a question in the chat and I can try and read that.
John, this is Jack Sharp, and it was really a great review, a really good overview of the situation. I just had a couple of specific questions. There's something that the NGS suppressed heights in 2021. What did that mean?
Sure. So essentially what they did was they said, they're recognizing that subsidence has occurred, for many years across the greater Houston area, and that those marks, those elevations that we're taking essentially are no longer valid across much of the study area. So what they did is, if you go to their webpage, essentially those elevations are no longer shown if you go to the individual pages for those benchmarks. Mm-hmm. Now you can click on the show superseded elevations and you can see those, but under the main page, those no longer show up. And what the only ones they show are essentially those core sites at the extensometers and a few other locations where those have been proven to be stable.
Okay, thank you. And one other this is really fascinating. It looked like some of the areas are still going down very, very slowly. And have you or anybody calculated the compression, recompression, and secondary compression indexes for these systems?
Sure, it's a great observation. I have not, but it's a very compelling topic, and I believe there is some active research going on to that end. Between that and then taking a look at that national, that creep consolidation between both of those. So yes, that is still going on. I have not calculated.
Okay, thank you.
John, excellent talk, really fantastic. So Houston has converted to mostly surface water use now, is that correct?
That is correct. There are multiple kind of regulatory areas that Harris-Galveston as Subsidence District has established, and regulatory areas 1 and 2 are largely converted over. Regulatory area 3, which is in northern, northwestern, and western part of Harris County, is due to a conversion here in 2026 for quite a bit of the water use. Once Loose Bayou gets completed and that water infrastructure will be available. So yes, that is moving kind of north, northwest, and west, those conversions over to surface water.
But Louisiana, I mean, maybe you're not involved in that. They're still using a lot of groundwater and seeing a lot of subsidence, so they haven't moved in that direction yet. So it's much more critical in that region. Is that correct?
As I understand, yes. I have not looked that whole lot, but that's my understanding.
And I guess one last question, Arizona saw a lot of subsidence, then they brought in the Colorado River water, and then that subsidence kind of stopped, and now the long-term drought, so they'll be moving back to groundwater in the Pinal area. It'll be interesting to see how much groundwater they can extract before they start seeing subsidence again.
Sure, very much so. I mean, once that pre-consolidation head or the maximum effective that stress gets exceeded, then you'll start to see that subsidence and that compaction occurring again. Yes.
Thanks a lot for an excellent talk. Really appreciate it.
Yeah, absolutely. Thank you.
So, John, would you, from your work here, and some of the key takeaways. And maybe some of this work's been done, but could you map out, say, the rest of the Gulf Coast sort of as a predictive way, percent sand maps, the, amount of pumping, and, or, sort of to be able to sort of risk assess different areas, or has that been done?
So there is a model called the Coastal Lowlands model. It's being developed that models land subsidence across the Gulf Coast. It's in development with USGS, and a subset of that model, the Gulf Coast land subsidence and groundwater flow model, it'll be published tentatively on November 10th, includes a subsidence process where historically subsidence is calibrated to in time, and then the model is used as a predictive tool. So yes, the ModFlow code that was developed by USGS has a subsidence package, multiple versions of it that have come out through time, where you can do exactly that. You input a number of input parameters, percent sand, the clay thickness, and you model that, you calibrate that subsidence through time, and from there you can use that as a predictive tool.
Okay, well, I think we're approaching the hour here, so I really thank you for your talk. Unless there's somebody else, Justin, are you wanting to jump on? Okay.
Yeah, I was just going to say, so I actually grew up in Deer Park. So I'm intimately familiar with the subsidence over the years, with family and everything. And it's just really interesting to, hear it broken down in a scientific way. So that was just really fascinating. So that's not so much a question, just great talk, loved it. I did have one question. I think I heard, the question is, correct me if I'm wrong, I think the board is expecting or working with the USGS on a new groundwater availability model for the Gulf Coast. Is that right?
That's correct. That's the Gulf Coast land subsidence and groundwater flow model that tentatively will be published on November 10th. Yes. For the greater Houston area. It doesn't include Austin and the areas over there. That's just the northern part of the Texas Gulf Coast.
Awesome. All right. Thank you.
Hello.
Great.
Thanks, John, for the presentation. This is Chris. Just wondering about the recharge. If we draw in and assuming the aquifers also were being recharged, how come we are having subsidence if the aquifers are being recharged as we are withdrawing?
So basically the reason is because the rate of recharge there is exceeded by the rate of withdrawal, and you have that imbalance historically for a number of years. So because you have confining conditions near land surface across much of that greater Houston area because of the Beaumont clay, the presence of the Beaumont clay, which is quite thick in some areas, it means that essentially you don't have that surface percolation down to an unconfined area, that aquifer is confined. So the recharge has to travel from the outcrop area much farther north, down dip all the way through that heterogeneous aquifer system, all the way down to where the water use is occurring. So essentially, you've had a lot of water come out from storage through time, and again, because you have that, you have the issue where you have the pressure difference between the fine grain and coarse grain units. Again, they'll say that clay starts to compact because of those withdrawals.
Okay. Hey, John, there's a question in the chat here. It says from Wanhu Lee, says, thank you for the presentation. I'm just wondering, any efforts about land nourishment to protect the subsidence in terms of maybe restoration work?
Admittedly, I'm not particularly familiar with that, so I wish I could answer that better. But I'm sure there are some efforts. I don't particularly know what they are.
There has been considerable nourishment in the Galveston area, trying to maintain the beaches from subsidence and erosion.
Okay.
Could I ask just one more quick question?
Sure.
I promise it's a quick one. I just want to make sure I understood you correctly. You were saying, like, as I grew up in Deer Park, right? So if I heard you right, you said that the reason that the land subsidence in Deer Park and Pasadena areas was lesser than the subsidence over in the Baytown areas. Did I hear you right? It's two factors. One was that Baytown is down dip, and they're sort of getting some of the groundwater withdrawal from Deer Park, Pasadena. And then also number two was that there's more compressible layers over just across the ship channel in Baytown. Did I hear that right?
Essentially, and when I was making that comparison, that's more of Baytown versus like the Katy area or the Houston area versus Pasadena. Pasadena and Baytown have similar amounts of subsidence through time.
Mhm.
So Baytown is because yes, Baytown was affected by declines in groundwater levels in Pasadena and the Deer Park area. In the Evangel Aquifer, you didn't have any water use occurring in Baytown. And you can tell the compaction was occurring because remember we had two co-located extensometers. So all you do is you difference the compaction record between the shallow one and the deep one to figure out how much was occurring in the Evangel Aquifer. So you can actually see that record and figure out, determine exactly how much was occurring because of water use in that Deer Park and that Pasadena area. And yes, number two is it's due to the amount of fine grained materials in Baytown versus those other areas. Baytown is among the highest amounts of it.
Okay, great. Yeah, I just always wondered about that because, you know, the head contours, you know, they're pretty comparable, and they're, you know, Baytown and Pasadena are separated by just, you know, a couple miles of the ship channel there, but much more land slipping into the bay
Right.
there in Baytown than in Deer Park, Pasadena. Just always wondered why that was. So
Yes,
thank you.
Baytown is very concentrated. Yes.
Well, John, we've now reached 10 o'clock, so thank you very much for your time and an excellent talk. And where, like you say, you'll be able to get to the talk on our YouTube channel, so it'll be there for others to see as well. So thank you again for coming.
All right. Thank you very much. Appreciate the opportunity to present.
Thank you.